So in the last session, we started with construction of DC machines, and I enlisted a number of components of a DC machine. Start, you have the frame, the yoke, the pole, the armature, the commutator, and the brushes that actually form actually the major components of any DC machine. So apart from this, some other DC machines may have uh, tertiary components that may be required for some special purposes. As and when we study such DC machines, we'll be looking at such components as well. So also I talked about, we started with the winding, the armature winding, and I discussed with you there are two important windings that we'll be studying. One is the lap winding and second one is the wave winding. We'll be understanding the difference between lap winding and wave winding and how exactly we can produce, how exactly voltage produced by the two types of winding is different. So let's start with the rotor coil itself. Or the armature coil. Fine. So as discussed in the last session also, we actually place conductors in the slots of the armature. So a coil is basically consists of a minimum two conductors. So we can actually say these coils are actually diamond shaped and preformed coils. Fine. So you will actually have the terminals of a coil. Uh, this side, the sides of a coil are actually referred to as a conductor. So this will be called a conductor. So each coil actually has two conductors. Fine. Now when we actually wind the uh, when we actually wind the armature, we do not use single turn of coil. We actually wind multiple. We have actually number of turns of a coil. So it will look something like this. You'll be having second conductor in the same slot, then connected outside again. On this end also you'll have conductor here. So you can have a number of turns of this coil, number of conductors, number of turns of a coil. Each coil side is referred to as a conductor. You can have number of turns, and actually that's the practical approach is having you may have hundreds of turns. So the total number of conductors of any coil will be Z will be equal to 2 N C. Fine. This I will simply write 2N where NC, where NC Z is this will be used to denote the number of conductors, and N will be NC will refer to the number of turns per coil. So in this case, say for example we have 3 turns, and therefore you can say 2 into 3, you have 6 conductors for this case. For 3 turns you can say this coil has 6 conductors. Fine. Uh, so, but again, the armature is not made up of just one coil now. It will be made up of number of coils placed in different slots of an armature. Again, when you see a practical armature, it may have anywhere between anywhere above uh, 20 slots, 30 slots, 40 slots. So there will be a number of slots of an armature. So in each armature, and a coil basically is placed in, for a 2-pole machine it will be placed in 2 slots. For n pole machine it will be placed in n slots, depending upon actually the type of windings will be actually studying that, whether it's a lap winding or a wave winding. So now now you have number of coils wound in different slots of the armature. So in nutshell, the total number of conductors will be equal to 2 NC into C, where C is actually now number of coils on the rotor. Fine. So the total number of conductors will be equal to 2 NC, where N is the number of turns per coil and C is the number of coils itself. And each turn of a single coil has 2 coil sides and therefore referred to as 2 conductors. Now, normally, the coil will span an angle of 180 electrical degrees. That means if this is your north, this is your south, these are your armature slots, this is your armature slot and teeth. Fine. So if a coil is placed, if one coil side of a if one coil side of a if a if one coil side is placed in this slot, another coil side will be placed at this end. So therefore this spans, the coil spans over an electrical 180 degrees. I'm saying electrical 180 degrees, I'm not saying mechanical 180 degrees. That means this is for a case of a 2-pole machine. Now if it were a 3-pole machine, 4-pole machine, sorry, you had the north, you have a south here, you have a north here, fine. Again you will have coils, armature, rotor, and this is your armature here. So in this case, say for example this is your 4-pole machine. If a coil side, if one coil side is here, another coil side will be here. This is still 180 degrees electrical. This is still 180 degrees electrical, although it is 90 degrees mechanical only. Now why it is 180 degrees electrical? Because from one uh, under one pole, that is north, to another pole, that is south, the magnetic field will rotate, will still have a complete 180 degree rotation. So from this end to this end, the magnetic field will still complete one cycle of rotation. That's 180 degrees. That's up to this point, sorry. So from north to south, it will complete from 0 to 180 degrees, and from the south to north, then it will complete pi to 2 pi. That's a complete cycle. Similarly here, from north to south, the magnetic field will rise and then fall at this point, and then from south to north, it will again, the magnetic field will start on pi and end up at 2 pi. Similar will be the case from north to south. It will here, the magnetic field from north to south will rise and fall to pi, and then from south to north it will go from pi to 2 pi, and north to south it will again rise, and then south to north it will again, it will complete actually, this will be 2 pi, this will be 4 pi. So you can actually see what happens is, in case of a two-pole machine, the magnetic field uh, basically completes one cycle over the circumference of the armature. But in case of a four-pole machine, the magnetic field will cover two cycles over the complete armature. In case of a six-pole machine, this will be, it will complete three cycles. So mechanically, if so the mechanical angle and the electrical angle is different for such cases. Right? So you can see for a two-pole machine, the mechanical 180 degree also means electrical 180 degrees, because the magnetic field is going to complete 180 degree of cycle. Fine. So one side is actually under the center of the given magnetic pole. The other side is under the center of pole of opposite polarity. So even though the physically the poles, say for example in case of four pole machine, the physically the poles north and south, they are not placed 180 degrees, but still the magnetic field will cover and will cover 0 to pi, and from under the south pole it will actually cover to south to north, it will cover pi to 2 pi. This is how the magnetic field will be varying with respect to omega t in different machines. So electrically speaking, if theta e is represents the electrical angle and theta m represents the mechanical angle, so you can see, and P represents the number of poles. In two-pole machine, theta E is equal to theta M, but in case of four-pole machine, you can see that theta E is equal to theta M divided by 2. Theta M is equal to theta E divided by 2. That is actually 90 degrees mechanical is equal to 180 electrical divided by 2. Say here actually 180 degree electrical is equal to 90 mechanical. So you can actually say theta m is equal to theta e by 2. In general, theta e is given by P divided by 2 times theta m. Fine. So in this case also you can see, if you put P is equal to 4, 4 by 2, theta e 180 is equal to 2 into 90. Accordingly, you can derive the electrical angle or the mechanical angle for different pole cases. Again, a coil is actually placed under, one coil side is placed under the north pole, another coil side will be placed under the alternative south pole. So in this case, as you can see, in this first case, as you can see, it's placed 180 degrees apart, whether it's an electrical 180 degrees or a mechanical 180 degrees, fine. But in the second case, what you are seeing is, when a coil side is placed under the north side and another coil side is placed under the south, although it is still electrically, the magnetic field is still varying from 0 to 180 degrees, it will be in all the cases, because under the influence of north pole and under the influence of south pole, the magnetic field polarities will change, and then it does not matter how closely they are located, but the magnetic field here are uniformly located. We are having two different pole pairs of magnets, so it will vary exactly in this fashion as shown in this diagram. So this This is an approximate equivalent of the magnetic field variation. B is equal to Bm sine omega t. So again, under the influence of one north pole to south pole, your magnetic field is varying from 0 to pi. That's electrically 180 degrees, but mechanically it's only 90 degrees. So for a 6-pole machine, if you can see, you will have north here, you will have then south here, you will have north here, you will have south here, you will have north here, you will have south here. If these are representing your poles. So from this to this is an electrical 180 degree variation of magnetic field still, but mechanically it's only 60 degrees of variation. So this thing is important. The coil span is always 180 degrees electrical, though mechanically it may not always be 180 degrees. It will be 90 degrees, it will be 60 degrees, it will be 45 degrees. So this is actually known as the coil span here. So if coil spans 180 electrical degrees, the voltage in the conductor on either side of the coil will be exactly the same in the magnitude. Such a coil is actually referred to as full pitch coil. So if two coil sides are placed 180 degrees apart, electrical degrees apart, then it's referred to as a full pitch coil. But what we do is most often the coils are not actually placed 180 degrees apart, they are actually placed less than 180 degrees, and therefore they are referred to as short pitched coils. So why we basically do short, why the coils are placed short by 180 degrees. So this is actually done to improve the process of commutation. We'll be understanding the issues that are involved actually in the process of commutation later, and for improving that we go for short pitching. So in other words, you have coil pitch. Coil pitch is actually referred to as the electrical angle between the two coil sides of a coil. Fine. So if it is equal to 180 degrees electrical, it is known as a full pitch coil. If it is less than 180 degrees, it is short pitched or fractional pitched coil. So pitch factor is given by electrical angle of coil divided by 180 degrees into 100%. So if it's 100%, that means it is a full pitch coil. If it is less than 100%, then it's a short pitched or a fractionally pitched coil, and this is done to improve the process of commutation. So this is one thing. So most of the rotor windings that you will actually see are 2-layer windings. They can also be 4-layer windings, but mostly we often go with 2-layer winding. That means, in other words, in a slot you will actually see two coil sides of two different coils. Fine. So this will actually be this upper coil side will be of one coil, and this lower coil side will be of another coil. Fine. So these conductors will actually refer to two coil sides of two different coils. So this is if there are only two coils in two coil sides in a slot, there it's known as a 2-layer winding. There can be 4 layers, there can be 6 layers, but most often we go with 2 layers. Then there will be actually number of turns of the same coil that will also be in the same slots, but generally two coil sides of two different coils are used. Then how many turns of two coil sides will be placed in this slot will vary from one uh, motor to another. Now, as we were talking about lap windings and wave windings, in case of a lap winding, I already said to you that what we do is that two coil sides of the same coil are actually connected to two alternate commutator segments. So if you lay a commutator segment flat, you will have number of commutator segments. So what we do is any two commutator segments will have one coil. Now there will be number of turns of this coil. You should get that. Uh, Two coil sides will be connected to. It can be there will be number of turns. It will be depending upon number of turns, whatever. Finally, the another coil side will be connected to an alternate commutator segment. Either it will be in this fashion or it can be in this fashion as well. Right? So you can actually see that in this case, the windings are connected to a forward commutator segment. So this will be known as progressive winding. The two coil sides are connected to forward commutator segments. Uh, but in this case, the second coil side is actually connected to the trailing commutator segment. So it will be known as a retrogressive winding. Now this here is known as, I'm referring to this as YC. YC is commutator pitch. So what is commutator pitch? Commutator pitch is simply the distance between, it will actually mean the number of segments that are between two coil sides of the same coil to which the two coil sides are actually connected. Fine. So in case of a lap winding, commutator pitch will always be equal to 1 because the two coil sides of a coil are connected to adjacent commutator segments. So always the distance between, in terms of segments, commutator pitch is denoted in terms of segments. How many segments of commutator are actually placed, are actually there, separating the two coil sides of a coil. Fine. So in case of a lap winding, this commutator pitch will always be equal to 1. So this is actually what we do in the lap winding. Now you have a coil that is connected to alternate to adjacent commutator segments. Once a coil finishes here, another coil will start from this commutator segment and it will end up at the next commutator segment, that is commutator segment number 3. Another coil will start here and it will end up at next commutator segment, that's commutator segment 4, and so on. So this actually I explained to you in the last session. So in case of lap winding, the coil sides are connected to adjacent commutator segments. The coil sides of the same coil are connected to adjacent commutator segments, and in such a fashion, that the next coil then starts from that adjacent commutator segment as well. So the coils will actually lap over each other, and that's why it's known as a lap winding. It's also known as series winding. Uh, Now what happens in case of a lap winding is there will be number of parallel current paths in the machine, and this number of current parallel paths will be actually equal to the number of poles of the machine. Right. Going back to the diagram of the lap winding that we saw last time. So we take this case of is actually a simple two-pole machine. We can also I will also show a four-pole machine. Fine. So here you can see a two-pole machine and you can see a four-pole machine. This is a two-pole DC machine construction, and this is a four-pole DC machine construction. Fine. So there's north and south. Here we have north, south, north, south. Fine. Uh, so I made the statement in a lap winding. There are as many parallel current paths as many as are the number of poles. So for a two-pole machine, uh, the number of parallel paths for current to traverse will be 2. For a four-pole machine, the number of parallel current paths, this will be only the case with a lap winding. The number of parallel current paths will be 4. For a six-pole, it will be 6. For eight-pole, it will be 8. Well, let's see what this actually means. Take this construction of a two-pole DC machine. Fine. So under the influence of south pole, the conductors, the current will be flowing into these conductors. So I'll be showing a cross here. I'll be showing a cross here, a cross here, a cross here. That means the current is flowing actually into the conductor. Fine. There will be cross here, cross here, cross here, cross here. And as I said to you, this is a two-layer winding. That means the upper coil side and the lower coil sides. Uh, these are actually two coil sides of two different coils. Fine. One is the upper coil side of one coil, and another one is the lower coil side of second coil. And in these conductors, the current will be flowing out of the page. So you can actually see the direction of current given by the right hand arm rule. So coil 1, this is coil number 1. The current is out of the page. That means the current is actually flowing in this direction in this coil. Fine. While as it's another coil side that's actually placed at that's actually this coil segment. Fine. This is coil 1. Coil 1. I will represent these coils first of all. Let me represent these coils. I'll be calling this 1, and I'll be calling this 1 dash. This is actually already done. This is 1 and 1 dash. 1 means the upper coil side and 1 dash refers to the lower coil side, and as is evident, these two coils are actually placed 180 degrees electrical to each other. Right? So 1 and 1 dash represent, and they are actually connected to two adjacent commutator segments. One is connected to commutator segment A, and 1 dash is connected to commutator segment B. Fine. So the current is flowing out of the page. You can say this is in this direction, and the coil in current 1 dash, the current is flowing into the page. So I will show it like this. Fine. That means it's actually moving out of this commutator segment, while as this current is moving into the commutator segment. Fine. In second coil, again, this is under the influence of north pole. Current is moving out of the commutator segment, while as its adjacent 2 dash, the current is moving into the commutator segment. For 3, the current is moving actually now into the commutator segment, while as for 3 dash, it will be moving out of the commutator segment. For 4, it will be moving into the commutator segment. For 4 dash, it's moving out of the commutator segment. For 5, it is moving into the commutator segment. For 5 dash, it's moving out of the commutator segment. For 6, it's moving again into the commutator segment. For 6 dash is this, it's moving out of the commutator segment. For 7, it's moving out of the commutator segment as it's under the influence of north pole. For 7 dash, it will be moving into the commutator segment. For 8, it will be moving out. For 8 dash, it will be moving in. 8 dash, this was 6 dash, 6 dash was this was 7 dash, this is 8 dash. Fine. 8 dash is in to the commutator segment. So these are the direction of coils in various coil segments. Now you can see what is happening here. Let us take commutator segment A. So there are two coils. One is actually 1 and 4. So in one segment, the coil current is moving in. From another segment, the coil is moving out. Current is moving out. At this segment again, the current is moving in and current is moving. The current is moving out and current is moving in. At C again, current is moving in, and while as from this, the current is also moving in. Fine. So this segment, the current is moving in from both directions. In segment D, current is moving in from one segment and current is moving out from another segment. At E, current is moving in from one segment and current is moving out from another coil. At this segment, at F, current is moving in from one coil side and moving out from another coil side. At G, current is moving out and current is moving out. Fine. So these two segments that are actually C and G, in one segment, current is moving in from both coil sides, while as at coil G, current is moving out from both coil sides. So the net resultant in all the other segments is actually 0, but at these two segments, either the current is moving in from both sides or current is moving out from both segments. We actually place brushes at these two locations. So whenever the commutator segment, the commutator is actually rotating alongside the rotor, so it will always happen whenever whether it is C or G, whether it's B or F, whether it's A or E, whether it's H or D, that are actually 180 degrees apart. Whenever they will be placed at this position, the coils, the two coil sides that are actually attached to these two commutator segments, the currents will either be moving in from both coil sides or be moving out from both coil sides attached to these commutator segments whenever they are exactly under the influence of north and south pole exact. Fine. So what happens is we place the brushes at these two locations so that from one brush the current is moving in or out, and from another brush segment the current is moving out. Fine. So the current and accordingly the voltage that will be available here will be having the polarity plus and minus. So current is actually moving out to the plus and uh, getting into the negative segment. So whenever the commutator segments will be exactly located at these two positions, it will so happen that the commutator segments, the coils that are attached to these commutator segments, the currents will be moving in and from both coil sides, as well as they will be moving out from both coil segments. So you actually have two paths in this case. That's actually under the influence of north and south. Now when we if we so you actually have two parallel paths. So there are a number of coil sides. So we can actually start with G. We can actually start with coil G. It is attached to 6 dash, while as at this end it's attached to 7, and 7 is then 3 dash is attached to D. From D is it is attached to 4. G dash 8 dash is attached to A. A is also attached to 1, so on. So there will be actually two paths. You have number of coils, but brushes will be located some in a fashion that, say for example, this is commutator segment G and this is commutator segment C. For this particular case, from one end coil, it so happens that from G the current is only moving out, while as from C the current is only moving in. In every other case, the current is actually moving out from one coil side and moving in from another coil side. So net current is actually zero at that current commutator segment. So there are actually two parallel paths because of the location of the poles and the nature of winding. This is clear for a two pole machine. But now what happens with a four pole machine? In this case, the current has already been shown to you. You can see all the conductors that are placed under the influence of south. The current is moving. The current has been represented by X. That means current is moving in. All those under the influence of north, current is moving out. For all these cases, current is again moving in. For all these cases, current is again moving out. Right? So therefore, you can say current is moving uh, into the page. Exactly, I do not. Current is moving into the page. Let's say it is this direction, and current is moving into the page, into the page, into the page, in, 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 in. For this case, it's out, it's out, it's out of the page, out of the page, out of the page, into the page, in, into the page or into the coil, out of the page, out of the page. Right? Let's start with A. So coils that are attached to A, in one case the current is coming in another case the coil current is coming out. So segment A is fine. Again with B, one coil side current is coming in, another coil side current is moving out. In C, at C you can see there are two coils that are attached here. In both cases, the current is moving out. Fine. So C represents one commutator segment where both currents are moving out. In D, current is moving in from one coil side, moving in from another coil side. At E, again in and out. At F, in and out. At G, you can see there are two coils. On both sides, the current is moving actually in to the commutator segment. Fine. H, I, J, again you will see in and out. At K, you will see two coils are attached, current is moving out. At O, again you will see two coils are attached, both in or out. Fine. So it really depends what is your into the page, and accordingly you will see that you can set the direction. So there are actually four commutator segments in this case, where the current is actually moving in from both coil sides or moving out from both coil sides. So in this case, there will be four parallel paths that will be produced, and in each parallel path there will be a number of coils attached. So with lap winding, what you can see is four parallel paths will be produced. Now plus and plus, what you can do is now you will be actually getting plus signs at two brushes and minus signs at two brushes. So what we do is then we actually connect these two pluses and produce a common terminal, and connect these two minuses and produce another common terminal, so that the net resultant plus and minus is available to us at the outside. We do not need four connections, we need only two connections, a plus and a minus outside. So both pluses will be combined, both negatives will be combined. But what we need to understand here is four parallel current paths are produced instead of two parallel current paths in this case. So depending upon the number of poles, what will happen is number of parallel paths will be produced. So number of parallel paths is represented by A in case of a DC machine, and therefore for lap winding, number of parallel paths will be equal to, for a lap winding, number of parallel paths is equal, A is equal to P, that's the number of poles. Fine. So if in each parallel path the current is I, total current that will be produced will be equal to 4I. Fine. And in each parallel path, the voltage across the parallel path is basically same. So we'll be having same voltage across all the four parallel paths. Now we have actually derived the voltage of, we know the voltage of one coil side is equal to VBL. Fine. So if you have connected at, if you have n number of coil sides connected here, so this will be equal to NVBL. So this voltage will be across all the four terminals. So we'll be deriving the EMF equation later. So for a lap winding, you need to know now that the number of current parallel paths for flow of current will be equal to 4. Accordingly, you will be placing 4 brushes in this in case of a lap winding. So for a P pole machine, number of brushes for a lap winding is P, as well as number of parallel current paths is equal to P. Fine. So we have discussed about coil sides, number of conductors, how we basically calculate the number of conductors, and what will be. So in one conductor, actually, the voltage induced is VBL. So if there are Z number of conductors, Z will be actually represented the, we have actually derived Z for total coils in the machine, that is equal to 2 into N into C. Fine. Now what will be the number of conductors in one parallel path? That the number of conductors in one parallel path will be Z divided by A. And if VBL is the voltage induced to one coil segment, total EMF that will be induced here will be equal to Z divided by A into VBL. Fine. So we'll continue with discussing the DC machines, and we'll understand what happens in case of a wave winding in the next session.